Hello everyone, welcome back to our educational video. Today we are going to discuss the last point which are remain from crystal field theory. In previous video we have covered most of the topics from crystal field theory. Now we will discuss about the relationship rehydration energy, that is solubility, with the stability of complexes. So the rehydration energy is equal to charge upon radius, is the only factor that affects the strength of the association and the stability of complexes. When drawing the relationship between them, we find that in theory we get the straight line passing the point of origin and delta value of the difference between practice and the theory. If we raise the value of delta from the practical value, we get the theoretical value. Look here into the graph. Here the energy rehydration is on the y-axis, and the d orbitals are on the x-axis from d1, d2, d3, d4, d5, d6, d7, d8, d9 and d10. So in theoretical way, if you look the graph, if you plot this graph, then it will be a straight line from passing the origin. And if you go through the practical way, then the graph will show you the rise of hump at the d3 and at the d8, and also the value of delta is increases from d1 to d3 and decreases from d3 to d5, again increases from d5 to d8 and decreases from d8 to d10. So this is how the growth of this value of delta is showing by practical way. So the difference is there between the theoretical concept and the practical value. So the factor affecting the stability of complex is energy rehydration. The first is charge, second is radius, and the third is delta, value of delta. Note of the image equal to the theoretical value and practical value. When d10, d5, d0 is there, where it is equal to 0. Color in coordination compound. One of the most distinctive properties of transition metal complexes is their wide range of colors. Yes, this means that the sum of the visible spectrum is being removed from white light as it passes through the sample, so that the light that emerges is no longer white. Means there is a type of, or we can say there is a absorption or removal of a light when removal of white light as it passes through the sample, so the light that emerges is no longer white. The color of the complex is complementary to that which is absorbed. The complementary color is the color generated from the wavelength left over. If a green light is absorbed by the complex, then it appears as a red. And the color in the coordination compound can be readily explained in the terms of crystal field theory. So consider, for example, the complex titanium, where the hexadentate ligand water molecule is there, and the charge on this complex is 3 plus. So this complex is violet in color, and this is an octahedral complex where the single electron, that is Ti3 plus, is 3d1 system in the metal d orbital is in the T2g level in the ground state of the complex. Next higher state available for the electron is empty Eg level. If light corresponds to the energy of yellow green region is absorbed by the complex, it would excite the electron from T2g level to the Eg level, and T2g1 Eg0 goes to the T2g0 Eg1, means the electron is excited from T2g level to the Eg level. Consequently, the complex appears violet in color. The crystal field theory attributes the color of the coordination compound to DD transition of the electron. So DD transition is also one of the most important concept for explaining the color of the complex. For example, aqueous solution of Ti3 violet, that is TiH2O6 3 plus, is violet due to the absorption of a visible light transmission of electron from a T2G to Eg level, and they absorb yellow light and passes the blue and red light. Now let us have a new concept, that is magnetism. CFT also explains the magnetism of the complexes. The magnetic moment can be measured using a Gauss balance. If we assume that the magnetic moment arises entirely from unpaired electron spins, then spin only formula can be used to estimate n, the number of unpaired electrons. This gives a reasonable agreement for complexes of the first row of a transition metal. Spin only formula is given as mu s is equal to square root of n in bracket n plus 2. Once the number of unpaired electron is known, either the VBT or the CFT can be used to work out the shape of the complex. Let us have an example of cobalt 3 plus in strong field with no unpaired electrons. So it is diamagnetic in nature. Cobalt 3 plus in weak field having 4 unpaired electrons. So therefore mu s is equal to under root 4 in bracket 4 plus 2. This will give you 4.9 Bohr magnet. Bm is the unit of spin only, that is mu s, which is Bohr magnet. So CO3 plus, that is cobalt 3 plus in strong field is with no unpaired electron is diamagnetic in nature, but cobalt 3 plus with 4 electrons in weak field is paramagnetic in nature. Now let us have a look on success of crystal field theory. Successful theory in the interpretation of spectral and magnetic properties. Since crystal field theory successfully explains the spectral properties, that is the color of complexes, and magnetic properties, that is diamagnetism or paramagnetism or ferromagnetism, so that is why this theory is a successful theory for interpretation of spectral and magnetic properties. Then second, it was able to explain the color of complexes transition element due to the difference in energy between the orbits of a non-equivalent complexes in the transition elements is relatively small, and it becomes possible to rise the electrons from low level to high absorption of a visible light. And this is the reason for the emergence of the color in the complexes. Now, whether there are successful interpretation by the crystal field theory, but it also have some limitations. So let us have the defects of a crystal field theory. The crystal field model is successful in explaining the formation, structure, color, magnetic properties of a coordination compound into a large extent, but however, from assumption that the ligand are point charges, it follows that the anionic ligand should exert the greatest splitting effect, and the anionic ligand actually are found at the low end of the spectrochemical series, so in low field. So this is some controversial point. Then second, further it does not take into account the covalent character of a bonding between the ligand and the central metal atom. So these are some of the weaknesses of CFT, which are explained by the ligand field theory, LFT, and molecular orbital theory. So VBT VBT means valence bond theory. So there are some limitations of valence bond theory which are overcome by crystal field theory, and these are some limitations of crystal field theory which were overcome by ligand field theory and molecular orbital theory. So molecular orbital theory is a successful theory, and we will see what exactly molecular orbital theory explains and structure of the complexes, spectral properties and magnetic properties of the complexes of transition elements in our next video. Till then, thank you and bye bye.